Let's continue talking about calculating limits using those limit laws. So we'll start with another example. Let's take the limit as x approaches 0 of the square root of 1 plus x minus the square root of 1 minus x all over x. As you can see, direct substitution isn't going to work because that would cause us to divide by 0. We can't just factor and try to cancel like factors, so we'll have to do what we did in that last example in the last video where we multiply by the conjugate. So we'll multiply our numerators together and we'll multiply our denominators together. Now, when we distribute, everybody in the first group gets multiplied to everybody in the second group, just like last time. This square root of 1 plus x times the square root of 1 plus x will be the square root of 1 plus x squared. Then we'll have the square root of 1 plus x times the square root of 1 minus x. We'll have negative square root of 1 minus x times the square root of 1 plus x. Those two middle terms will cancel, and then we'll have minus that negative, or that square root of 1 minus x times the positive square root of 1 minus x. And so we'll end up with this first term squared and this last term squared being subtracted. So when you square a square root, they end up canceling. Now notice I'm subtracting this entire product, or this entire thing squared. So what I'll need to do is square it first, the square root and the square cancel, then I'll need to subtract each of those terms and distribute that negative. And when I do, notice that we have this one and this one are going to cancel. So we have 2x up top, and then we still have x times that conjugate in the bottom. Well, now this x and this x are going to cancel, and we just got rid of the culprit that was preventing us from being able to do direct substitution by plugging x equals 0 in. So now we can try that direct substitution, and we end up getting 2 over 1 plus 1, which turns out to be 2 over 2, or 1, which is a real defined value, so this limit does in fact exist. It just didn't exist using direct substitution. We had to multiply by the conjugate to get there. And these are just little different methods that we have to use in order to evaluate these limits. Let's look at another example. The limit as x approaches 3 of 1 over x minus 1 over 3 all over x minus 3. Now notice, if we tried direct substitution, that would give us 0 in the bottom. Well, we can't factor. We can't use a conjugate here. So what we're going to do is actually just try to combine these fractions with a common denominator. So I'll multiply the top and the bottom here by 3 and the top and the bottom here by x to get a nice common denominator of 3x. Once the denominators are the same, I can subtract their numerators over that denominator. And I'm going to go ahead and switch this 3 and this minus x so that the x term comes first. And now what I'm going to do is, this is minus x plus 3. I'm actually going to factor a negative 1 out of there. So when I factor out a negative 1, I have a positive x and a negative 3. Now if I distribute that negative 1 times x gives me that negative x. Negative 1 times negative 3 would give me that positive 3. Now let's look at this x minus 3 in the denominator. Dividing by something is the same thing as multiplying by its reciprocal, so dividing by x minus 3 is the same thing as multiplying by 1 over x minus 3. Now notice this x minus 3 and this x minus 3 are now going to cancel. So this whole limit is really just the limit as x approaches 3 of negative 1 over 3x. Now I can try this direct substitution, and I get that this limit does exist, and it's equal to negative 1/9. So methods that we are going to need to use in order to be able to calculate limits. Direct substitution. If you get a real defined value, you're done. If not, try factoring. Cancel any like factors, then do direct substitution. If that doesn't work, you may just need to simplify. You may need to multiply by a conjugate, or you may need to find a common denominator. So there's a bunch of different methods that you're going to have to practice for taking these limits. Now, one of the things that we've already talked about in previous lectures is that the limit as x approaches a of f of x is equal to L if and only if the lower limit and the upper limit are the same and they both equal that real value L. So where is this going to come into play? When we start talking about things like your piecewise functions. Now we've talked about piecewise functions before, so let's take a look at this one that has 3 pieces and let's graph it. So we're going to graph this top piece here for all values less than negative 1, this middle piece for all values between negative 1 and 1, and this piece here for all values greater than 1, and pay attention to where the or equals are. Now remember, when it comes to graphing piecewise functions, you have to plug in the value of the split into both pieces and determine if it's going to be open or closed. So for that top piece here, 3x minus 2, we'll start with negative 1, plug in negative 1, and we'll see that's less than negative 1, so it's non-inclusive, so that gets an open circle. Then you can plug in any values you want as long as they're less than negative 1, like negative 2 and negative 3. For this middle piece here, we got to start at that split negative 1. When we plug in negative 1, notice negative 1 is less than or equal to x. That has the or equal to, so that's going to get a closed circle. And then we'll plug in this value of the split 1, and then we determine since that's less than, that's going to get an open. And we can plug in any other value we want as long as it's between negative 1 and 1, like 0. For this bottom piece, we'll start at 1. Since it has the or equal to, that'll be closed, and then you can pick any other value you want as long as it's bigger than 1, like 2 and 3. Once you get these ordered pairs, we can graph it, and this is the graph of that piecewise function. Now let's talk about the limits of these piecewise functions here. Let's talk about the limit as x is approaching negative 1. Remember, there's two ways to approach negative 1. You can come from the left, from below. So as I'm approaching x equals negative 1 from below, my function is approaching negative 1. You can approach negative 1 from above, from the right, and as you do, coming from the right, my function is approaching 1. Now notice my upper and lower limits don't match, so that means that the limit itself does not exist, and we would call that DNE, does not exist. Now let's take a look at the limit as x approaches 1 coming from the left. It's 1. Let's look at the limit as x approaches 1 from the right. That's also equal to 1. Since the lower limit and the upper limit both match, then the limit as x approaches 1 itself does in fact exist, and it is also equal to 1. So when we're talking about taking the limit of piecewise functions, we have to be very, very careful of these values where your piecewise function is split. So let's take a look at another example. Let's look at the function f of x equals the square root of 4 minus x for all values that are bigger than 4, and 8 minus 2x for all values less than 4. Now, the first thing I want you to notice is that this function is not defined at 4. There is no or equals to. Remember, limits don't care what happens when you plug the c value in. Limits don't care if your function is defined at that c value. What a limit says is, okay, if I want to take the limit as x approaches 4, I want to know as x gets really, really, really close to 4, what does f of x get really, really, really close to? Now, remember, for a piecewise function, this one has two pieces. At the split here, either the two pieces will meet, in which case, yes, the limit will exist, or the two pieces will not exist, which means your left and your right-hand limits won't match, and therefore the limit would not exist. So let's take the lower and the upper limit. If we were going to take the limit as x approaches 4 from above, that means we're plugging in values that are a little bit bigger than 4, like 4.1, 4.01, 4.001. So I want to know what is this function doing as x gets really, really, really close to 4, but from values just a little bit bigger. If I'm a little bit bigger, I'm going to use this top piece right here. So to take the limit as x approaches 4 from above, I'll try direct substitution into this top piece. Square root of 4 minus 4 gives me the square root of 0 or 0. Now, if I want to take the limit as x approaches 4 from below, I'm plugging in values that are just a little bit less than 4, like 3.9, 3.99, 3.999. I want to know what is my function doing as x is getting really close to 4, but coming from values just a little bit less. So I'm going to use this bottom piece right here. And I'll try direct substitution. 8 minus 2 times 4 gives me 8 minus 8 or 0. Now notice the limit from the right and the limit from the left are the same. That means the limit itself does exist, and so the limit as x approaches 4 of f of x is equal to 0. Let's try another one. Here's a piece that has 3 pieces, a piecewise function with 3 pieces. So let's take the limit as x approaches negative 1. We will have to take our upper and lower limits. When we take the limit as x approaches negative 1 from the left, that's values a little bit less than negative 1, we're going to use this top piece right here. So I'll try direct substitution into that top piece, and I get negative 4. Now, if I'm going to take the limit as x approaches negative 1 from above, that's going to use this piece right here. So I'll do direct substitution into that middle piece right there to get negative 1. And what do you notice? The upper limit and the lower limit do not match, so that means that the limit itself does not exist. Now let's look at the limit as x approaches 3. If we're going to take the lower limit, that's for values just a little bit less than 3, we're going to use this middle piece right here, and I'll do direct substitution. If I want to take the upper limit as x approaches 3, that's for values just a little bit bigger than 3, I'll use that bottom piece and try direct substitution. Now notice the limit from the left and the limit from the right are the same. That means the limit itself does exist and it's equal to 7. All right, one more example to finish up calculating limits using the limit laws. Let's evaluate the limit as x approaches 0 of the absolute value of x over x. Let's talk about the absolute value of x. The absolute value of x is the distance from 0. So if x is negative, the absolute value would be a positive, which x is already negative. To make a negative positive, it would be a negative negative. So we'd stick a negative in there, right? If x was negative 1, the absolute value of negative 1 would be 1. Well, if x is negative 1, to make that negative positive, it's negative negative 1. And if x is positive, well, then the absolute value of x is just itself. So now let's look at the upper and lower limits here. The limit as x approaches 0 from below, that means you're approaching 0, but you're coming from values a little bit less, which makes x negative. So that means x is negative, which means the absolute value of x is negative x. So this limit as x approaches 0 from below of the absolute value of x over x would be the limit as x approaches 0 from below of negative x over x, which reduces to negative 1, and the limit as x approaches 0 from below of negative 1 is just negative 1. Now let's look at the upper limit. The limit as x approaches 0 from above. That's coming from 0 from the right-hand side, which means that your x values are a little bit bigger than 0 or they're positive. So the absolute value of x would be x itself. This reduces to 1, and the limit as x approaches 0 from above of 1 is just 1. Now notice these upper and lower limits don't match, so it turns out that the limit as x approaches 0 of the absolute value of x over x does not exist. That's it for calculating limits using those limit laws, and I'll see you for the next video.